In this Von Mises stress video, I'll briefly talk about how to derive a certain criterion, the Von Mises criterion. And the Von Mises criterion is the equation that I've been keep using. Alright, the Von criterion is the equation that we have constantly been using. This equation, if you still remember, 1 over square root 2. Right. So I'll somewhat derive in a very short manner to show that this is how it's derived and what is the meaning of this thing. Alright. And let's go. We know that this particular shape is the shape that tells you that any stresses acting over this criterion will be considered unsafe. However, the Von Mises one states that if you have any points lying on this thing, you are still considered safe, right? If you were to exceed, then you are considered unsafe, right? So the Von Mises actually touches on, in fact, all the criteria actually touches on this particular boundary. Alright, so it states that all your certain stresses is equals to your U strength. Alright, it's equals to all these boundary layers. Alright, such that when you have to bring this over to the other side, alright, is xy minus the sigma is equals to 0. On the other hand, sigma minus sy is also equals to 0. Alright, if sigma is later on will be larger, right? But so let's put it in this way first because it's easier later on. Alright, and let's start off with the plotting of what we're gonna do. Alright, so therefore, if you still remember in the previous video, we talked about the Deriving stresses, or your shear stress of your U stress. Alright, the shear component of your whole system, whole criteria that ensures that it doesn't fail. So this is somewhat the criteria, and the middle one is your U stress, and then the rest of the shear stresses we call it the KY. Alright, you still remember, like principal stresses, the Deriving stress has its own invariance that is shown over here, and then I crop it out. But if you have to compare the J2 to our J2 over here, this whole thing is in fact the J2. This is from the textbook. Alright, well, this one is from your PDF that we have taken out. 1 over 6 sigma 1 minus sigma square, as you can see, it's totally the same. Alright, this thing is totally the same over here. While we're missing some terms, you actually forget to put it. So this is something that you need to be aware of, be careful of also. But why do we take J2? Why not we take J3? Why do we put J2 over here? It's because, as you can see, this thing is in terms of the order of square, alright, which is very big if you were to talk about it. And then very big plus a very big one divided by 6 will give you somewhat a bigger number than divided by 1 over 27. You get what I mean? So you're dividing to 27 compared to dividing by 6. This value will always be larger than J3. Alright, if you were to put in terms of a matrix, you know that J1, J2, J3, J2 will always be bigger than J3. Alright, this is what we have proved to you in like saying that this is the largest stress, and then this is the lowest one, and then it's somewhere in between. And we know that J1 itself is equals to 0 because there is totally no so-called normal stresses if you were to talk about it. So hold on, if you were to come back to this Deriving stress, this portion over here is simply 0. So if you talk about sigma 1 1 plus sigma 2 2 plus sigma 3 3, then it's simply 0 plus 0 plus 0 is equals to 0. That's all. Alright, so J1 itself is simply equals to 0. Alright, and therefore we have somewhat known that the maximum shear that may occur is the J2. Alright, because we are actually keen to find, because we say that the shearing will cause deformations. Right, the pure shearing will cause deformations, and we're going to compare the shearing, the shearing equation that is in relevance to this own invariant. Alright, we're going to minus away the ky that we have derived earlier. Alright, the ky which is the Deriving stresses. So this ky over here, this particular ky over here. So if you were to do that, the first thing first, because since we know that it's equals to 0, alright, with some relationship that sigma minus sy is equals to 0. So if your stresses is on this boundary, alright, you should be somewhat safe. So you assume that our J2 minus away our ky square is equals to 0. We're going to prove to you that this thing will eventually derive up to this thing. Alright, as I say, I'll be going through a fast case, so at least it will not bore you. But since this is equals to 0, alright, this is equals to 0, you can simply multiply 3. Alright, so if you multiply, sorry, I should be multiplying 3 over here. So 3 times 0 is still 0, and then 3 times 1 over 6 is actually half, and then 3 times your over here, you're simply times 3 over here, sorry. So you are simply minus 3ky square. Alright, so the first step is just to multiply everything by 3. Alright, so I don't know why, but let's continue first. And if you were to expand, sigma 1 can be expanded as sigma 1 1, sigma 2 can be expanded as sigma 2 2, etc. And then your ky can be expanded to your shear stresses. Yes, if you remember in the previous video, your sigma 1 2 square plus sigma 1 3 square. Alright, it can be used over here right now. Alright, and therefore as you can see, everything is in terms of square, square, square. So it somewhat looks like x square plus y square plus z square plus something, alright, blah blah blah, is equals to some arbitrary constant, maybe a square, right? Because it looks like a Pythagoras theorem to us, right? So in fact, therefore we can generalize this phenomenon, or this whole phenomenon, as a certain Pythagorean system. So this a square is something like your sigma m square, and this sigma m square is your von Mises stress, alright, so to speak. Alright, therefore let's continue. It is totally no meaning, but maybe in the mathematician world they would see this as a giveaway. For some reason, I don't know why it becomes like this and then like this, but at the end you derive something like 3 times j2. Alright, so our equation that we start off from j2, alright, minus your shear stress of your U strength, alright, in the end we'll derive, instead of something weird, we derive 3 times j2. Alright, go back to 3 times j2 by itself. Okay, and then this is actually sigma m. Alright, m square I should say. Alright, so if I were to rewrite this one as 1/3 sigma m square, alright, which is equals to j2, which is also equals to the j2 that we have seen here over here, we just sub in this value as our j2 now. Okay, as our j2 now, instead of all this chunk, let's sub in as 1/3 sigma m square. Alright, so therefore when I do that, I'll sub in over here, while the minus ky square, I actually keep it still. Alright, over here. So next, we also multiply everything by 3, because since we know that the y is equals to 0, so we multiply by 3, this one will become 3 over 3, it becomes 1. Alright, and then 3 times minus ky will be 3ky squared. Alright, so, and therefore since you know that y is equals to 0, then you can bring your sigma m square over the other side. So once you bring it over here, or I should bring this thing over to the other side. Alright, so once I bring it over here, I would have this one, alright, 3ky squared equals to sigma m squared, your von Mises, and then I'll just simply square root this whole thing. So what I will have is equals to square root 3 and then ky. So this square has been removed while the 3 is being square root. So your sigma m is equals to this one, and therefore it's the same thing as being written over here. Okay? Since we know that any stresses which is equals to your U strength starts to is the beginning of yielding. So at this point you're starting to yield, alright, but haven't yield yet. Anything larger than this, sorry, will be yielding will start. So therefore this stresses, any stresses, in our case I could sub in as sigma m, our von Mises, since we already found our von Mises. In the context, this thing over here is actually your sy. Okay, as you cancel this step also. Okay, so since your von Mises is equals to your sy, then you can simply write your von Mises, since you know that von Mises is equals to square root 3 ky, then your U strength can be re-represented in terms of this thing. Okay, So it's in terms of your shearing, so to speak now. Alright, therefore this is your Von Mises shear. Alright, this is your Von Mises shear. And to be more exact, if you want to see something, so 1 divided by square root 3, your U strength, you can write it as your sigma 1. So remember this equation is your Sy. In the previous video, we actually talked about it. Alright, this thing over here is our Sy. Okay, and therefore is your Ky. So this whole thing over here, 1 square root 3 times your U strength, your normal stresses or your hydrostatic U stress, is equals to the shear part of your U stress. Okay, so this thing over here is your shearing, and if you take a look, this thing is in fact inside your PPT. Alright, it's should be this one, this thing over here. Okay, and so in the previous video we also show you that sigma 1 is equals to 1/3 of your hydrostatic. Alright, which is over here. Alright, these are all your sigma 1, sigma 2, 2. But if you minus away your 1/3 hydrostatic, which is your initial U strength, you would say. So sigma 1 is in fact your sigma 1/3. I mean 1/3 sigma h, 1/3 sigma h, and 1/3 sigma h. Will give you your U strength, so to speak. Alright, and therefore if you were to look in your PPT over here, this is your sigma h. So you plus all your stuff, and then you divide it all by 3. Alright, therefore this is your normal component or your hydrostatic stresses. Alright, and then if you were to take your Ky, this is your Ky, your shearing, you're gonna minus away your normal component using, because all are in terms of vectors, so therefore they are squaring, and then in terms of a Pythagorean system, what you have is a shear component of your devioteric. We can call it the devioteric, pure shearing of the component itself. Okay, so this step over here is simply to remove the middle portion of your matrices. If you remember, this is some stress tensor, your minus of hydrostatic, ensuring that this whole thing over here is equals to, not equals to but rather than trying to remove all the normal stresses, such that you only have a certain shear stress left over. Alright, so we actually do quite a lot of stuff to actually prove this thing. Alright, although there is a little blurry part somewhere. Alright, because as you can see, since we say that this is somewhat the Ky, then how about this thing over here? This is also Ky, that's what we derive, what. So that's why there's a pretty much blur thing. That's why I don't want to go into details, but at least you see some link between them. So this is the purpose of me to create a link first, so in the future if you were to watch it again, and then at least you know something more, then you can just redo a new video or something like that to build on. So we are ready to go into the next parameter, alright, to derive the next stuff. Since we know that they are all in terms of a sigma h now, these are all hydrostatic. Alright, and the curvature is all here, stating that is your boundary, your criteria. If your point is within, or okay, I'll just pick any point. I'll just pick this point as we call it point P. This point is somewhat being built by a sigma h over here, another sigma h, and another sigma h. This is the normal point. Alright, sorry. And then you can pick any arbitrary point over here. So the difference between them, alright, will give you the overall understanding that are you inside this stuff over here. Because so far what we've been doing just now, alright, is to actually derive the shearing part only. We only derive the shear components of the Von Mises, so to speak. So it's not totally there yet. Alright, not totally there yet. In other words, this is the shear component. Alright, so we want to derive this thing. Alright, this is our Von Mises equation that we've been keep using. Alright, and therefore now what we're touching on is the more critical part. Alright, which is to relate the understanding there is in fact the relationship between any point with regards to the boundary part of your criteria. Alright, so it's your somewhat your U stress criteria. So if its U stress is equals to certain sigma, then you're at this particular line over here. Anything larger than that, you're gonna be yielding, alright, so to speak. Therefore, we can illustrate any point from your origin to your point over here. Any point, you can have point over here, you can have point over here. So you can represent any point in terms of a vector. So OP from origin to your point is equals to ON plus your MP. Alright, so ON is actually the normal or the stresses that is within your boundary. So this stresses is somewhat like this. Alright, so to speak lah. Alright, so this is the boundary at a point. So this point, the difference between this boundary point comparatively to the arbitrary point that you choose is MP. Alright, so we can actually write in terms of ON plus MP. Okay, so you will have OP over here. So I'll set up this equation to relate the point with regards to your criteria that is within this thing. Alright, this shaded part. Take it as the ON is simply the end point is actually the hydrostatic magnitude. Alright, sigma h. Alright, let's carry on first and see how it goes. Alright, same thing, we use the Pythagoras theorem because we want to find the vector. So you need to use the Pythagoras theorem. And your OP is any arbitrary stresses. That's why you can simply write sigma 1 squared plus 2 squared plus 3 squared. While ON is your hydrostatic stresses, which are all this, because there are sigma h, there are 3 sigma h, so therefore they add up together. Alright, you have 3 times sigma h squared over here. Alright, we also know that sigma h is equals to 1/3 sigma 1 or 1/3 sigma 2, etc. Alright, which is in the previous video. Sigma 1 is equals to 1/3 of a sigma h. Alright, so it's being rewritten as 1/3 times sigma 1 plus sigma 2 plus sigma 3. Okay, that's why it's kind of a bit so-called messy, right? That's why luckily I do this referencing, at least it's easier for you to see. So this whole chunk over here is simply your 1/3, your sigma h lah. Okay, and then this is so your whole sigma h is squared. Alright, so if you were to multiply it in, you expand it out, you have 1/9 all the stuff over here. Okay, and then this 3 times 1/9 will give you 1/3. Alright, the rest is still the same, and then you somewhat rearrange, put them all together, you have something like this. And then you continue to do this, you have 2/3 times your sigma Von Mises square again. Alright, so to some extent, this is your related to your Von Mises already. In fact, this part is the blurry one, but never mind, let's continue first. And eventually you'll derive that your MP, alright, from your this point, the criteria point to whatever point that you want is equals to square root 2/3 times your Von Mises. Okay? In the previous part, we say that sigma m, the Von Mises, is equals to your U strength, which is equals to square root 3 ky. Alright, this OK is in fact ky in the text. Alright, and therefore we can simply sub your Von Mises over here, alright, as your sigma 3 times ky, since we know that Von Mises is equals to this thing. Right, so if you were to sub it in, what you have is this thing over here. Alright, so it's in other words square root 3 ky. Alright, so if you were to cancel out, because this is square root 2 over square root 3. Alright, so if you can cancel out each other, what you have left is square root 2 times ky, which is this 0k is your ky lah. Okay, so therefore your MP is equals to your square root 2 ky. And if you to bring it down, 1 over square root 2 MP is equals to your shear component. Alright, for some reason your MP itself is, in other words, your is with regards to your shearing portion. Alright, this thing over here, the one that we keep using. Alright, so therefore this is just a pretty big brief of how to derive the Mises U criterion. And the Von Mises criterion, as you can see, is talking about taking any point with regards to your criterion and see how your point will behave with regards to shearing. Alright, so at least you get a feel of how the Von Mises is dealing with things. For some reason, your Von Mises criterion is in fact is of this shape over here. Okay, octahedral. Right, this is some of the octahedral plane. If you talk about octahedral shear stress, it's a Von Mises one because your plane is an octahedral. In other words, this is some of the 3D stuff. Alright, for octahedral. And this particular this thing over here and this plane will give you a shape like this. Alright, which is this particular one. Alright, this plane over here. Alright, so if you were to deal with other planes, you will create something like this. Alright, that deals with other stuff. So you're actually creating all this octahedral stuff, but we are simply talking about only this particular plane. Alright, and therefore it's somewhat lying just at the octahedral side of the stuff. Hopefully this is pretty clear. Instead of the curvature like this. Alright, and therefore in the next video we'll talk about the Tresca one in a very fast manner. Before I shall see you there.